Hi there! Once again, we find ourselves sitting here next to my iPDS, Personal Development System. This thing is like the world's fanciest EEPROM programmer, but it's also a complete development system with 2 CPUs. You can run 2 things at once, you can compile stuff, you can assemble stuff, and of course you can program your EEPROMs via the built-in EEPROM programmer. Now, I've already done a video on this, so people are going to say, well, why did you do another video on the iPDS? Aren't we done with the iPDS? Well, there were a couple criticisms on the last video, and I actually listened to the criticisms. One of them was that I talked a lot about how this thing is capable of doing 2 things at once, and then I didn't really show it doing 2 things at once. They said if you say it's going to program an EEPROM while doing something else, why didn't you program an EEPROM while doing something else? So I'm going to do that. I don't know if it's visible here in the current light, but it's actually running Conway's Game of Life, so we will program an EEPROM while playing Conway's Game of Life in the background on the other CPU. And that's the nice thing about this computer, is that it does have these dual CPUs. So back in the day, you spend a lot of time running your compiler or programming your EEPROM. You'd like to be able to get some other work done while you're doing that. So the other criticism I got was, hey, you build a speech synthesizer for every vintage computer project. Everyone gets a speech synthesizer as your canonical first thing. Why is there no speech synthesizer in the iPDS? Well, I went ahead for this video and I'm going to show you guys a speech synthesizer. And I'll show you some sound cards for it as well. So we will play a 3-voice sound, the theme music from Beverly Hills Cop on this iPDS from like 1982 or so. So what I'm going to build are some little multi-modules like this. They're actually adaptable to any, not just this computer, but any multi-bus computer from back in the day. They kind of plug in. This here is a AY38910 one. What I have installed here and what I'm going to demo will be a 76489, the CSG soundboard, as well as an SPO256 speech synthesizer. So you'll see a little bit of design on those 2 boards, and then you'll hear them playing some music and speaking some words, and then of course we will program an EEPROM. Okay, here is the speech synthesizer board. So over here we have the multi-module bus. So this is a little pin header that goes between the multi-module itself and the multi-module adapter, or the multi-bus board, or whatever you plug it into. It's a very simple bus that they invented back then. So you've got 8 data bits, 3 address bits, an IO read, an IO write, a reset, and a chip select. So chip select comes on, IO read comes on, you're reading off the data bus. Chip select comes on, IO write comes on, you're writing to that data bus. You've got 3 address bits here, which let you select 8 different addresses in your peripheral in case you need to address things. There's actually a couple of chip selects. I only, because I was doing the SBX 251, bubble memory is where this started. I only marked one of them here on my connector, chip select 0. There's also a chip select 1, which is right alongside of it. So, if you needed another 8 addresses, you could go with the second chip select. There are a couple of interrupts. We don't need those for this example. And there is this sort of presence detection here, this MPST. I'm not sure what MPST stands for, but basically you pull it low to indicate to the computer that the multi-module is installed. Down here I have a programmable logic device that just handles the addressing and anything else for that. We basically take those signals from here, IO read, IO write, chip select, the address bits. We put them into here, and from that we can trigger the address load bit on our speech synthesizer. Our speech synthesizer is the SPO256. 8 data bits, an ALD, which is your address load, that strobes data into it, a load request or a standby, which are the status bits that go back. Those status bits, they come into here. I've hooked myself into the data bus on D0 so that I can actually use this thing, this PLD down here as an input buffer as well. So this here gets you the digital interface to the speech synthesizer. Now, for the sound output, but we've got, an LM358N with a couple of filters here. These resistor, capacitor filters meant to filter out the highs. So we have kind of a low pass filter. I kind of figured that out myself from some online calculators. I hope I got it right. We've got a line level output. You've got a volume control, actually 2 different places for the volume control. You've got coming over here going into an LM386 audio amplifier where you've got an onboard speaker or an audio out jack. Now, one thing you'll notice in all of the boards I'm talking about today, there is a mute circuit as well. The LM386, if you take pin 7, which I think is a bypass capacitor pin, and you pull that low, you will mute the audio amplifier. So that gets pulled down by this transistor, hooked up to this mute signal, which connects to this PLD here so that we can, by writing the right bit to one of those addresses, we can mute the audio amplifier. Okay, and very, very similar. This board here is a 76489 based soundboard. Now it has the 76489 chip here. I think it's a very small chip, if I remember right, just 16 pins. Data bus, chip select, write, ready, because you actually have to wait until it's ready before you can stop writing to it. Clock, which helps it do the musical notes at the right frequency, and an audio output. Now, all of the audio output circuitry over here is the same from my speech synthesizer board. And the multi-module connector is the same, and the PLD is almost the same. Where this differs is in this this latch here. Reading the data sheet, when I looked at this 76489, it says that you have to keep the data on the bus until it deasserts the ready line. So what I do is when you're writing to it, I stick the data in this latch, I latch it, and I keep that latch outputs flowing to this chip until the ready comes up. And that's coming back in here. That's kind of synchronized down here through the PLD. So a little bit different from the speech board in that I had to do this latching thing. One of the properties of the 76489 is that when you power it up, it will emit an obnoxious tone out the audio output. It has no like power on reset or anything like that. The obnoxious tone just comes out, goes through all this, boom, 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 comes out your speaker, and there's an obnoxious tone coming out of the computer until you can get around to writing the register. So that is the reason why I added the mute to all of my LM386 audio amplifiers, was for that 76489 sound chip. Okay, one last board to go. This one here is an AY38910 based soundboard. Now the AY38910 is another 3-voice plus noise sound chip. To me, I didn't notice a lot of difference between that and the 76489, so I'm probably only going to demo one of those for you here in this video today. But just know that it was connected very similar to the other projects. We've got the multi-module bus over here. We've got some data lines. We've got the PLD, which handles our addressing stuff. This one's a little bit weird in how you address it because it's got this BC1, this BDIR, and this BC2, which configure whether you're doing register writes or data writes. So a little bit of logic down in here to fire those signals at the right time. You can check the PLDs. I'll put them all online. But we've got the big chip here, big 40-pin chip, hooked up to the data bus, and those signals. Out of it comes 3 music channels, which you have to kind of combine through some resistor networks to kind of mix them together. Then comes out, I skipped the audio filter on this one, ran out of room for it on the board, and sent it straight in, through the volume controls into the LM386 and out into the speaker. So like I said, very similar to the other 2 boards we've already seen the schematics for. So my multi-module adapter had spots for 4 modules. The bubble module took up 2 spots. But that leaves 2 more spots, so I started to make some other modules. Here we have a speech synthesizer. Here we have a CSG sound card, that's a 76489. And here we have an AY38912 sound card. So we'll take a look at each one of these in a little bit more detail. But each one of them is similar. You've got a connector, goes out the back, that will plug into the multi-module adapter board. I have these nice shrouded ones here. I ran out of shrouded ones. That one's got a cheapy one there. But anyway, let's start going through these boards. So first of all, the speech synthesizer. So speech synthesizers are kind of my thing. Every vintage computer I build a speech synthesizer. Typically I build a speech synthesizer using the SPO256A-AL2 chip. That's this one here. It's not my favorite speech synthesizer chip. That would of course be the Votrax. But it is the cheap one that you can get still on eBay, so I have some of those, so I always build an SPO256 board. There's our SPO256. It's got a 3.12 megahertz crystal. I've got an op amp here that does some filtering on the output, and an LM386 audio amplifier. Finally, there is one chip here that is a PLD, a GAL22V10D, that does the address decoding and also handles the passback of the status. This thing works by sending phonemes to it. Each phoneme is a basic sound, and then polling until it sees that the speech synthesizer is idle. So you just sit there in a loop, you output a phoneme, you poll until it's free, and then you output the next phoneme. You've got a volume control. You can either mount it here or here. The speaker, I had several different options. On this one, I put on this little piezo speaker. It mounts nicely on board, just like that. Now, this one here is a sound card based on the CSG. That's the 76489. I believe that thing was popular in the Tandy 1000. It's this little guy here. He's not a very big chip. I think he's only about 16 pins. It's got a crystal to drive it. Again, we have LM386 audio amp and an op amp that does some signal conditioning. I again have a GAL22 V10D here that handles the I/O, decode, and associated logic. And I have over here a latch. I used a different kind of speaker. This is a little magnetic speaker here, this round one, pigtailed over here to connect up to the audio out. I should mention on any of these boards I put in the provision for audio jacks here or here for line out or speaker out. This one I actually mounted the audio jack. And then finally we have one more sound card. This is the AY38910. It is also a 3-voice synthesizer plus some noise options, I believe. I don't know as much about programming this one, but you look up the data sheet, you can figure out how to program it. Much larger chip. It actually has some I/O ports built into it, so you can run joysticks or something. I believe there's an RC 2014 sound card that uses this. I kind of looked at that for some inspiration. So again, we've got the sound chip here. We've got a crystal to do the oscillator for it. Over here we have, typical of my other boards, I have a GAL22 V10D that does the address decoding and such. No op amp this time, but there are lots of capacitors here that do some mixing because this thing actually outputs 3 independent channels, so we got to kind of mix them together. LM386 audio amplifier, and another one of these little tiny magnetic speakers. Okay, let's go ahead and mount these boards to my multi-module adapter. You can see this is the iPDS motherboard. We've got the second CPU board over here. We've got my multi-module adapter board there, together with the bubble memory module in slot 1. That leaves slots 3 and 4 free. So we'll just take these and put them in. We'll start with the speech synthesizer board. And you do want to make sure you get it lined up properly, because the way these connectors I use fit, you can actually get off by one. But if the screw hole lines up, it is right. So let's go ahead and plug that one in. Check the screw hole. The screw hole is good. And then down here in slot 4, we will put the complex sound generator. Right about there. Now I need a couple of 632 screws. Okay, and now we can take this whole assembly and reinstall it in the iPDS. And here's our board. For posterity's sake, here's what the front side looks like. Okay, let's go install. Okay, let's go ahead and boot up. There we go, it's accessing the A drive. We will boot the A CPU from Bubble. Now if we look over here, the B CPU is sitting here waiting also, so we will also boot the B CPU off Bubble. And now we've got our A4 prompt up there. That's the A CPU, and down here we will get our B4 prompt. Now I wanted something that continuously can run in the background, so what I did is I ported my Conway's Game of Life implementation from the 8008 to the 8085. So let's do a Life R12. And here we are on the B CPU running Conway's Game of Life. Now we can let this continuously run. Well, I switch CPUs. It's actually running up there. Let's make the window a little bit bigger. And there we go. We should be able to see Conway's continually running on the B CPU while we're down there on the A CPU. So let's program an EEPROM. I have here a 2732A inserted in the EEPROM programmer. I'm going to need to use my floppy drives for this. So let's run the PROM programming software. It is on the floppy F1 called iPDS. Type 2732A is what I've got in there. Copy. fourth 25.IUP to buffer. How about that? Let's see if it likes that. Okay, so checksum 4277, we've loaded it into the buffer. Then we will copy buffer OFFF to prom. Oh, so this is actually going to burn that 2732 EEPROM, and we will see that as we are doing this, the Conway's Game of Life continues to run in the background. Okay. It did not work. Let's make sure we got our chip installed properly. We do. Let's do a blank check. Prom. It's blank. Okay, this time it's going. Maybe I didn't have the prom properly engaged in the socket. We can see it is writing. I've actually got the red light on over there at the prom programmer, and we've got the Conway's Game of Life running there in the B CPU. So I'll just let it sit here and program for a while, and then we'll come back and we will have shown how this thing is able to do stuff in the background while we're programming an EEPROM. Okay, the EEPROM finished programming. The checksum is correct. So there we go, programming an EEPROM while running Conway's Game of Life. Okay, so we're continuing to run Conway's Game of Life. Let's look on here. I've got some other programs on here. I've got, for example, I've got a song program which will use the sound card. So let's do song. I've just built a few songs into it. Some of the songs are single voice and some of them are three voice. So let's try some of the single voice ones. So song B, your traditional boot music for this type of computer. That ought to sound familiar. Let's try William Tell Overture. Mary Had a Little Lamb. And let's try some multi-voice music. So let's do Axel F. This is going to be in three voices using the full capabilities of the 76489 sound chip. Here we go. Okay, that was the music player. Let's try the speech module. So I've got a program here called Say. It's my traditional text-to-speech for the SPO256 speech synthesizer. Scott was here. This is my personal development STEM computer.
This is my personal development system computer.
How about like system ready?
System ready.
Your EEPROM is programmed. Sir? Why not? May say EEPROM wrong. Let's see how it does. Okay, it kind of said EPROM, which I guess that's good enough. Anyhow, that is the speech synthesizer. And of course, you know, these things, we could run these continuously. Let's do, let me look at song. I think I've got a continuous flag. Try song. Let's do continuous. And we'll do Axel F. And Merry Christmas. I think I can make it play them both. Now, switch CPUs. Here we are in Game of Life. I think if I escape, did I make it? Yeah, I made it so we can quit. Make the other screen smaller. So, I mean, that's pretty cool. You know, it really is a dual CPU computer from back in the day. I can certainly do two different things at the same time. Anyway, I hope you had fun seeing the iPDS again. So, I hope we corrected the oversight last video, which was not really showing off the multi-CPU capability in this vintage computer. And I hope we also properly demonstrated adding a speech synthesizer to it and a sound card to boot. Thank you. Please subscribe. Thank you for watching my video. Please visit my website at www.smbaker.com for more electronics projects and sandrail stuff. Bye.